In this movie we are going to talk about the comparison of two means. This is a very useful tool, and you could say that it's probably the most used statistical tool worldwide, because we often have two groups and we wish to compare the two in terms of whether their means are equal or different. So the learning objectives of this lecture is that you should understand the ingredients in the t-test, be able to calculate the t-test based on descriptive statistics, be able to test data with both variance homogeneity and variance inhomogeneity, understand the relation between a confidence interval and a corresponding test. And then at the end you should be able to understand that the concept for the t-tests can be generalized to all sorts of tests for answering other types of questions. So we are dealing with this setup where we have a population of people and we wish to know about this population, but the fact is that we are not able to characterize the entire population. So what we do is we sample from it, so taking a small part of it out. We do some statistics on this sample, descriptive statistics here in terms of mean, standard deviation, and so forth. And then we say, well, these measures can be used to characterize the entire population, and we call that inference. And the testing part, the t-test and all sorts of other tests, work with the part down here, the inference part. How much can we say based on the small sample concerning the entire population? So here I have a small example. The example is that we have ethyl acetate in wine from two different countries. So we wish to compare whether Australia is higher in this content of this aroma component compared to Chile. So the task here is that you should use a couple of numbers, so pause the video and contemplate about what numbers are interesting here, which descriptive statistics are interesting in comparison of the two distributions, Australia and Chile. So comparison of means, there are three scenarios in general. There are the scenario where the two groups, Australia and Chile, have the same standard deviation. And that is that we say the spread in the data are the same. And that doesn't seem to be the case here, right? We can see that the standard deviation for Australia seems to be a little higher than compared to Chile. We also have a scenario where we have different standard deviation. So we wish to compare the means of these two groups, and we allow there to be a difference in the standard deviation between the two groups. So Australia having a higher standard deviation compared to Chile. And then the last scenario for the t-test is the paired observation. So where we have samples in each group which belong to each other, for instance, from the same individual. So here is some intuition. We wish to compare two means, and here we have a sample y, sample 1 and sample 2, and two different scenarios. So over here we see that there is a difference in the mean, but there is also some variation. Over here we have the same difference in mean. The mean here is 4 and the mean here is 5, and the standard deviation is much smaller. So a test over here should reveal that there might be some differences, whereas a test over here should reveal that there certainly is some differences between the two groups, simply based on the standard deviation being different between the two scenarios, small here and large here. We can do exactly the same where we have the group over here sustained and the groups here, they are having way higher standard deviation. So a test here should probably reveal that there is not so much to gain in terms of difference of the means, because the standard deviations within each group is so large that we cannot test them. So what we learned from this small example is that although the difference between the means can be the same, we need to take into account how widely distributed the data is. Is it small, medium, or really high? So here goes. Here is the model formulation for a t-test. So I have two groups, x1, 1 up to x1 in 1. That's the first group. And we say that this group is normally distributed with a mean and a variance. The same goes for the second group, x2, 1 up to x2 and 2. And it's also normally distributed with a mean and a standard deviation, or a variance here. So what we wish to compare is the two means, and we do that by formulating a test statistics, and it looks like this. So what it is if you want to compare the two means, a natural way to compare the two means is to take the difference between two means, and if this difference is different from 0, so either very negative or very positive, a large number, we will say that the means are not equal. And then we scale that difference by some measure of the standard deviation. So what this is that we have a pool standard deviation and then a square root of something which measures how large are the distributions that we use, or the samples that we use to making the statistics. So let's see how this is done on Blackboard. So I have two distributions. I have two samples, x1 up to x1, 6, and x2, 1 up to x2, 8. And for each of these groups, I calculate the mean. So the mean in the first group is 9.2. The mean in the second group is 8.3. The standard deviation in the first group is 1.1. And in the second sample, it's 0.9. So here I have the descriptive statistics that I need to do the test. And further, I know how many samples are going into calculating these descriptive numbers. So it seems like there is a difference between the two means. So x1 is slightly higher than x2, 9.2 is slightly higher than 8.3. So the first thing we need to do here is to calculate what is called the pool variance. And the pool variance, or the pool standard deviation, is a weighted average of the observed standard deviations. So here is how it's done. So the pool standard deviation is, if we take the individual variances and then we multiply by how many numbers have gone into calculating this variance, and we do that for the two groups. So here is the variance for the first group, variance for the second group, and we weigh them by how many numbers, how many samples have been used to calculate these two entities. And then to get rid of this weighing factor n1 minus 1, n2 minus 1, we simply divide by n1 minus 1 plus n2 minus 1. And this is the pooled variance. So it's basically a weighted average between the variances, and if you calculate this one, you will get 1.0. And what you see is that this one should be in between the two observed standard deviations. So 1 is between 0.9 and 1.1. If you get a number which is larger than the largest or less than the smallest number, you know that you have calculated wrong, because you can't get an average which is outside what you're averaging over. So now we have the pool standard deviation. We can go further and calculate the statistics. So we refer to this as the observed statistics, and what we do is we take the mean of the first group, subtract the mean of the second group, we divide by the pooled standard deviation, and then we have a square root which tells us something about how many samples have gone into this calculation. So this is 9.2 minus 8.3 divided by 1.0 times 1 divided by 6 plus 1 divided by 8. And if you do the math for this one, you get 1.67. So now we have test statistics. And we wish to know if this test statistics is probable meaning that could we observe such a large number here, given that the two samples, x1 and x2, are from the same distribution. So the intuition is that if you get a large number here, then it's probably not the case that these two samples have the same mean. And if you get a small number, a number around 0, then it means that the difference between the means are very small, and so we would assume that they could come from the same distribution. So what we would like to calculate is a p-value. So the p-value tells us something about how probable it is to observe a value larger than the observed, and then we do like this. So what we have is a t-distribution that's a bell-shaped distribution. It's centered around 0, and then we have the observed here, t-obs. And what we wish to know is the area here is how probable it is to get a t-value given that the two samples are from the same distribution. We use the numeric sign here, which tells us that we basically just should multiply by 2, because you can deviate from being equal by also having this area over here. T larger than t-obs equal to, and then we calculate this area. We can use a program like R to calculate how large is the proportion in the t-distribution. So the command is pt, and you chug in the number that you're interested in, 1.67, and then the number, the degrees of freedom, which in this case is 12. This will give you the cumulative distribution, but what you're interested in is the probability of being higher than 1.6 and not less than 1.67. So you say 1 minus this number, and that gives you 0.06. So if we go back here, we say that this one is 2 times 0.06 equals to 0.12. So this is the p-value for this test. And what we say is that although that there are some differences between the means of these two groups, it seems like that is still likely to happen, that we observe drawing 6 samples from one group, 8 samples from another group. It's 12% out of the occasions, given that the means are the same, this would happen. So we conclude that it's not very likely that the two groups are very different. A quick note on the t-distribution. So in this case we use the t-distribution to translate the t-statistics, the test statistics, to a p-value. So the t-distribution is this distribution which is taking into account the difference between the normal distribution and the observed distribution from some numbers sampled based on how many samples that you have used. So if you use a lot of samples, so for instance if you have degrees of freedom 30, you will approach the normal, the standard normal distribution, whereas if you have lower number of samples you will be deviating from it. The t-distribution takes, so to speak, into account how well the standard deviation is estimated by taking into account how many samples are used to calculate the statistics for the test. Instead of making a t-test or a test statistics, you could also go in and make a confidence interval on the difference between the means. And the confidence interval for the difference between the means is based on the same ingredients as the test. So what you do is you subtract the two means from each other. That is your best guess at what is the difference between the means. And then you, around this plus minus, put an interval. And this interval is scaled by a t factor, telling how confident, what is the probability confidence bands that you want to use. and alpha here tells you something about how large a percentage you want to be outside the confidence interval. Then you have this pooled variance or pooled standard deviation and multiply it by how well the data is estimated. So you will see that instead of calculating this fractile, you will, as you do in the test, you'll use a certain number, which you can calculate by this command in R, to get a confidence interval around the mean. In this case, the difference between the means. So let's see how this is done in R. So what we've written here is how to calculate the confidence interval. So we take the difference between the means plus minus t fractile, the standard deviation pooled, and then this square root of how well or how many samples have you used to calculate this statistics. So it's 9.2, that's the average from the first group, 8.3, that's the average from the second group. Then the t fractile in this case is 2.18 multiplied by 1.0, and then the square root of 1 over 6 plus 1 over 8. And if you do the math of this one, you'll get that the confidence interval is 0.9 plus minus 1.2. So that means that this confidence interval goes from minus 0.3 up till this one added together is 2.1. So what we see is that this confidence interval for the difference between the means overlaps 0. It goes from negative to positive. So it basically gives the same answer as the test, that the difference between the means being 0 is likely because it's encapsulated by the confidence interval, and that is also what the t-test statistics shows us. So we see that these two are compatible, reflecting the same type of information. In this case, we have used something called the degrees of freedom, or DF, and which tells us something about how well the variance or standard deviation is estimated. And you can think of it as how large a sample do I have, so how large is these two numbers N1 and N2. And if we have, say, 1,000 observations, we know that the standard deviation is pretty well estimated. On the other hand, if we only have 3 observations, it's not that well estimated. So that is what is going into calculating this fractile from the t distribution. In the case where we say, well, we cannot assume that the variants are the same. For instance, here we will say, well, Australia is having a wider distribution than Chile. We use something called the Welch t-test. So what it does is that it tests the test statistic slightly. So instead of having the S pooled outside here, we get the individual standard deviations or variances put in divided by the number of samples used for calculating it. So you'll see that this is pretty much going to be the same number as the in the case where we use the pool standard deviation. The second thing that's changed is the degrees of freedoms. They become smaller compared to when we pool the standard deviation, and you calculate them by this equation down here. And when the degrees of freedom become smaller, it means that also your test becomes slightly weaker. The last case that we could talk about is where we have two groups. For instance, here we have 14 observations from the same people at baseline and at time 30 days, measuring some marker. And we know that these measurements are from the same people, so there is a relationship between the two columns here. Then we use what is called a paired t-test, and it's pretty simple to do. What it does is that you calculate the differences, so you subtract 4.27 from 3.81, and that gives you a new value. You do that for all the observations. And then that new value, what we call a delta value, is used for calculating a confidence interval or a test. So what we do is we actually lose the original observation, the original data, and only work with these delta values. We do this setup is pretty common, and we do it because it's powerful in reducing the random variation. And the variation that we can take out here is the stuff that is related to the individuals. So the fact that I look more like myself, even after some given intervention, than I look like everybody else. So in summary comparison of two means, we have these three scenarios: two groups with the same variance, two groups with different variance, and two groups where the observations are paired. The test statistics is based on the difference between the means divided by a relevant measure of deviation. That's the test statistics. Then we take that test statistics and translate it into a p-value using the t-distribution. So the cookbook goes like this. You get some data and you visualize it. You can visualize it by a box plot plus jitter plot, for instance, or two histograms. If you have paired data, then connect the points or make a scatter plot. Consider whether you should transform the data prior to any testing. So for instance, using the log transformation or the square root transformation to get the variances to be more similar. Then you evaluate whether the standard deviation is similar or different between the groups, simply by looking at data. And then you identify if the observations are paired. Then you make a confidence interval for the difference between the means, and maybe chuck on top a test for the possibility that this difference is equal to 0. And as we talked about, that these two, the test and the confidence interval, should basically show the same conclusion. Then you comment on your results.